Okay, good morning. I too am delighted to be part of this extraordinary mission. And as this first slide suggests to you, I'm now going to change your focus from these fascinating planetary systems to the stars that they orbit. See, it's important to understand that to a large extent, we only really understand the extrasolar planet systems as well as we understand the stars. Fortunately, Kepler is not only a spectacular mission in terms of its planet-finding capabilities, but it's equally spectacular in terms of its capabilities of studying the stars. And consequently, there are hundreds of astronomers across the world engaged in studying stars using the Kepler data. You don't have to take my word for that. This pie chart shows you, in rough numbers, the ratio between the number of papers published on stars and the ratio number of papers number of papers published on planets. And so clearly, Kepler has an enormous impact on stellar astrophysics. And I want to also point out to you a very nice article written in the recent issue of Science News about stellar astrophysics with Kepler. Now, I'm here to tell you about the first result from a specific study, the Kepler cluster study, for which I'm the principal investigator. A primary goal of the Kepler cluster study is to develop a way to determine the ages of stars and their planets. See, a star and its planets form together and share the same age. So if we can determine the age of a star, we also have the ages of its planets. Now, let me give you an example of why that's important. This is a star. Our ultimate goal is to find a planet around this star, like the Earth, a rocky planet, at the right distance so that life as we know it might have a chance to exist. Right away, the question arises,
How old is it?
How old is this star? Because we know from studying our own planet that if the star and the planet is about 1 billion years old, only the most primitive microbial life might exist. If they're 3 billion years old, well, maybe slightly more complicated life exists, but certainly nothing that a SETI-like program on another world would pick up on. But nonetheless, something that might change the atmosphere of that planet. Is it perhaps 4.6 billion years old? Well, all of a sudden we know we could have a planet teeming with complex and intelligent life. And is it older yet? We don't know what to expect. So clearly, the question of age is highly relevant to the question of life. Having said that, it turns out that determining the age of a star has proven to be one of the most difficult tasks in astronomy. And the reason for that is that a star like our Sun, as well as the vast majority of stars we find planets around, look almost the same throughout most of its lifetime. I try to illustrate that with a chart up here. You can see the star from 100 million years to about 10 billion years looks almost the same. That is to say, the observable properties of a star, like mass and size and temperature, are nearly constant throughout its lifetime. This is important, and to drive this point home to you, let's imagine that if the same was true for humans. Let's imagine that we were born small babies, as we are, but on our 1-year birthday, we looked like an adult, and we stayed looking the same through our 20s and 40s and 60s, all the way up to 80 years old. And then all of a sudden, we appear old, like the stars. In that case, you couldn't just walk down the street and look at someone and guess their age. You would actually have to ask for their birth certificate. Right? And look at it and do the math to find out how old they are. Well, stars do not have birth certificates. And so we're faced with this task, this challenge of finding something about them that does change steadily and gradually with time, and that we can observe. there is one such property. The spin, the rotation of a star, it changes, and it changes gradually and steadily with time. And so we can use the spin rate, the rotation rate of a star, as a clock to measure its age. This clock has not yet been built. It's not yet been put together and adjusted so it can keep time well and give us the right ages of the stars. And so it is the goal of the Kepler cluster study to build this clock and to calibrate it so it can give us the right ages of the stars. And we want to do that by measuring the spin rates of stars for stars of which we already know the ages. What do I mean by that? What I mean is that we want to measure the relationship between the stellar spin period, the time it takes a star to spin around once, and stellar age. This diagram shows you what we currently know about this relationship. On the horizontal axis, you see the stellar age in billions of years. On the vertical axis, you see the stellar spin period in days. So stars who spin fast are found in the lower part of this diagram, and stars who spin more slowly, the older stars, are found in the upper part. Now you might ask me, how can we know the ages of some of these younger stars represented by the purple curve down here in the lower left corner? And this is where the word cluster in the Kepler cluster study becomes relevant. Star clusters are families of stars born together who share the same age. And today the only thing I want you to remember about star clusters is that we can determine their ages well, and thus the ages of their stars, by measuring and plotting their colors and their brightnesses and examining the pattern we see. And so the purple curve in the lower left corner represents measurements of the spin periods of stars in young star clusters. But that leaves a big gap out to the only star for which we know something about this relationship beyond 500 million years, our own sun. And so it is the goal here. If we want to measure the ages of older stars using this relationship, we need to measure spin periods of stars in older clusters, and that is where Kepler becomes critical. See, the way we determine the spin period of a star is by measuring the periodic changes in its brightness as dark spots on its surface move across the phase, back on the backside, and across the phase again. Young stars spin fast, just like a top on a table, and they have big and many spots. And so, as you see in the left panel here, the brightness fluctuations of young stars are large and of short duration and relatively easy to measure. But as stars get older, they spin slower and they have smaller and fewer spots. And so the brightness fluctuations, as you can see in the mid panel and the right panel, get smaller and of longer duration. And that is what we want to measure. That is our goal. We want to measure the spin periods, these brightness fluctuations for old stars in old star clusters. And that is where Kepler is critical to us. So we have now taken the first step toward this goal. We have measured the spin periods in a 1 billion year old cluster and thereby extended this spin-age relationship to 1 billion years. That still leaves a 3.6 billion year gap out to the sun. But our next target of study is a 2.5 billion year cluster within the Kepler field of view. And there's even a 9 billion year old cluster in the Kepler field of view that will allow us to extend this beyond the age of the sun. And so when we have measured this relationship between stellar spin period and age, we can go back and look at all the planet host stars, measure their spin periods, use the relationship to determine their ages. And this is how Kepler can help itself in regards to the question of planetary systems and life by studying stars. Thank you.